Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about covalent bonds. Okay, this will probably be the longest video in this series. Okay, this will be pretty lengthy. If there's parts that you understand, you can skip ahead, or if you feel like you're struggling with each part, don't be afraid to go back and rewatch segments about this, because there's multiple topics we're going to cover. Okay, so I want you to write down this definition for a covalent bond and a molecule. So a covalent bond is a nonmetal atom that shares some or all of their valence electrons to form covalent bonds. Okay, covalent bonds are atoms that are sharing electrons. Okay, and a molecule is basically an atom or a molecule that is being held together with covalent bonds. Okay, this is different than our ionic bonds that we learned about earlier. Okay, we actually don't call them molecules, right? We don't call NaCl a molecule. We actually call it a compound, right? We're now being a little more specific with our definition. So a molecule is a neutral group of atoms held together by one or more covalent bonds. See that covalent bond part? That's the thing that makes it a molecule. Okay. For example, if you have oxygen, we know that oxygen is diatomic, meaning it exists in pairs. And those oxygen atoms are actually sharing electrons with each other, and they're forming a molecule, and you're breathing in molecules. Okay? All right. Do not worry about this bottom part, this hybridization. Okay, this just complicates your orbital structures. They actually form hybrids with each other, and that's what gives rise to specific structures like methane and having 4 different bonding angles. Okay, and don't worry about this. This is more advanced chemistry, but it won't be required for this class. But if you want to read through it, you can. All right. So let's get into this. All right, so the octet rule when it comes to molecules, all right, if we look at fluorine, okay, fluorine on our periodic table, I'll just grab mine. I've been referring to this quite a bit. So if you look at fluorine, how many electrons does it need to have a full octet? Well, if it needs one more to become like neon, so it's probably going to gain an electron. It needs to gain one more to satisfy that octet rule. If you need a review of the octet rule, go watch the video Ionic Bonds. I've talked about it in that video, okay, in the very first video of the series, okay? And you'll notice that fluorine is missing 1 electron, and it needs to get one more, okay? There's a little formula they have here. It's 8 minus 7. That's referring to 8 is the total number of electrons required for a full octet. 7 is how many it has, so it needs 1. It's going to form 1 covalent bond. Okay, and fluorine we know is diatomic in nature, so fluorine is actually going to pair up with another fluorine, and it will share that 1 electron with each other. So if I cover up one of these fluorines, do you notice how my fluorine has all 8 electrons around it? And if I cover up the other side, can you see how this one has 8 electrons? So the octet rule is satisfied because they're sharing. Okay, remember how I broke up the periodic table into 2 groups? We have our givers and our takers. Okay, these elements that are nonmetals tend to take electrons to form octets, while these ones tend to give away electrons to form octets, specifically the alkali metals and earth metals. Okay, okay. So now when we're looking at molecules, we're typically only looking at nonmetals. All right. So if we look at fluorine, right, they can't steal from each other. They'd rather share with each other, and we'll actually talk about electronegativity trends in a little bit further in this video. Okay, so let's do a couple more and just kind of get comfortable with the idea of sharing electrons. Okay, so hydrogen, okay, in order for it to have a full octet, it only needs 2 because it wants to be like helium. Okay, so hydrogen has 1 electron, and it wants to have 2 because it wants to have a full octet. And for it to share with another hydrogen, they're both going to satisfy their octets. You see how this one has 2, and then if I flip my hand on this side, this one has 2. All right, so we're paying attention to this octet rule. We've done the fluorine example, all right, but in this example, we're actually being a little more specific in our drawings. And instead of drawing 2 dots, we're going to draw a line in between the ones that are being shared. Okay, we're going to call these ones on the outside lone pairs. Okay, these lone pairs, all right, exist around the atom, but they're not making a covalent bond like these ones are right here in the middle. Okay, so we're going to draw a line. So you can kind of imagine there's a dot on each end of the line to kind of signify it. That's kind of how I like to remember it. All right, now this one's a little harder. We have nitrogen and hydrogen. So if you look at nitrogen, all right, it's going to have 5 electrons, and it's going to need 1, 2, 3 electrons to be like neon. So it has 1, 2, 3 electrons that need to be paired, and it has 1 lone pair on the end. And if you look at hydrogen, it's happily going to want to share 1 electron. So we're going to need 3 of them to go and pair with each of these single electrons. So in this picture here, we can cover up all of our hydrogens, and now nitrogen is going to have a full octet. This hydrogen has a full octet, that hydrogen does, and the bottom one does as well. All right, so everything is satisfied, and now we're going to be a little more detailed, and we're going to draw a line in between our nitrogen and our individual hydrogens to show that they're being bonded. Okay. All right, now let's come down here. Okay, and there's some exceptions to this, and we're not going to talk about it in this class. Okay, there's some elements like phosphorus and boron that can kind of break these rules, but we're not going to talk about it, including sulfur. Sulfur is another one that can break these rules. You can actually form 6 bonds. Okay, let's flip over here. All right. Let's write out, I'm not going to have you pay attention to this down here, but I want you to write these definitions. A single covalent bond, a double covalent bond, and a triple covalent bond. Okay? So a single covalent bond is a bond made by 1 bonding pair of electrons. Okay? And a double covalent bond is a bond made by 2 bonding pairs of electrons, and a triple covalent bond is a bond made by 3 bonding pairs of electrons. You need to pause the video, pause it, and write down these definitions. Okay? And I can show you down here what that may look like, okay, in a single, double, and triple bonds. You may see that in a water molecule, we have a single bond here between oxygen and hydrogen. In a carbon dioxide molecule, we have 2 bonds being formed between each side of this carbon. And then down below, in carbon monoxide, we have 3 bonds being formed between carbon and oxygen. So there is more than one that can happen. And 3 is the most it can go. It can't go to 4. Okay? It's not going to. All right, they're going to form either 1, 2, or 3. But how do you know that that's what's happening? Well, we're going to describe that in our example. So I'm going to use some note cards here. I'm going to pull away, and I'm going to use my periodic table, and I'm going to draw out how we can align them as far as how can we draw dot structures for molecular substances. Okay, so our molecule that we want to draw is H2O. All right, and in this molecule we have a hydrogen, and they both have 1 dot around them because they're in the first group. And then oxygen has how many electrons? It has 6. So it's going to have 1, 2, 3, 4, 5, 6. All right, hydrogens both want to get 1 more electron. Oxygen wants 2. Okay, so the atom that can make the most bonds is going to be in the middle. So oxygen is going to be in the middle of our drawing. So we're going to have 2 lone pairs here. And we know that if you can kind of think about it, this hydrogen is going to want to bond here, and this hydrogen is going to want to share here. So we're going to have a bond that forms like this. All right, and this bond here is showing me 1, 2, 1, 2. So if we cover up my hydrogens, we've got 8 around my oxygen, and I've got, if I cover that line, I've got 2 electrons for each hydrogen. So the octet rule is satisfied. And they formed a single covalent bond. All right, let's do another one. Let's do one with a double bond. So let's do carbon dioxide. So CO2. All right, carbon is found in group 4, so it's going to want to form 4 bonds. Oxygen, there's 2 of them. And they're both going to want to form 2 bonds. So the atom that's going to be in the middle is the one that can form the most, and that's going to be carbon. So carbon's going to be in the middle. Okay, and if you look at our image, we can kind of deduct. So this is going to form. This wants to make 4, and this wants to make 2, and this wants to make 2. All right. You can see that maybe the oxygens here. Oh, I actually drew a dot there. That shouldn't exist. There's this one wants to form 2. Bonds, and this one wants to form 2 bonds, and this one wants to form 4. So what if we just did it like this? And we drew our oxygens out here. all right? And we could draw it like this. So if we look here at oxygen, how many electrons do I have around it? I have 1, 2, 3, 4, 5, 6, 7, 8. I go around my carbon atom, and I've got another 8, and then I cover up my carbon atom, and this one now has 8. All right? And we can draw these lines here to show a double bond is being formed. Okay, so this is a double bond. Okay? You will get better at this as you practice it. It takes practice to learn how to build these molecular models, these dot structures, because you're going to recognize what goes in the middle and then how many bonds can each of these different atoms form. Okay. All right, let's do another one. Let's do carbon monoxide. Now this one's a little trickier. All right. So if we look here, we've got carbon monoxide. It's just CO. All right, and we'll learn about naming, how to name molecules later. Okay, it's going to be in the next video. So carbon monoxide, it's going to have a carbon, and it's going to have an oxygen. Okay, this one's going to have 2 bonds. This is going to make 4. All right, and because there's 2 of them, there is no middle atom. Okay, because they're just going to be bonding with each other. So if we look here at carbon and oxygen, all right, we know that this carbon, this one is going to bond with this one, so we're going to have 1 bond. This one's going to bond with this one, so it's going to bond. All right. And then carbon's got these other 2 lone single atoms out here. And then oxygen's going to have 2 out here. So if we look here, is oxygen happy? Yes, 1, 2, 3, 4, 5, 6, 7, 8. All right, but if we look on this side, it's not looking so good over here. We've got 1, 2, 3, 4, 5, 6. This one does not have 8. So what we need to do is actually take one of these lone pairs, and it's going to be donated to the triple bond. So if I draw it now, it looks like this. Okay, and if I cover up my oxygen, I have a 1, 2, 6. So I now have 8 around my carbon. And if I look around my oxygen, I also have 6, 7, 8. So it's now happy. This rule about donating this is it's not common, okay? And I'm not going to expect you to know how to do that on a test. But when we're drawing triple bonds, sometimes we have to move things around in order for the octet rule to be satisfied. Okay, let's do one more. Let's do a little bit trickier one here. It's going to be let's do hypochlorous acid. So it's going to be let's do this. Let's do HOCl. Let's do this one. Okay, so we have HOCl. So we have hydrogen, which has 1 electron. Oxygen, it's got 6, right? Because we've done it several times now. And chlorine has 7. So it's going to have 1, 2, 3, 4, 5, 6, 7, like this. The one that can make the most bonds, this one can form 1, this one can form 1, and this one can form 2. So oxygen is going to be in the middle. All right, and we can kind of start to see how this is picturing up. So hydrogen is going to form 1 covalent bond with oxygen, and chlorine has 1 electron, and it wants to share, and it will share with the other oxygen molecule. So if we draw it like this, it's going to have 2 lone pairs, and then chlorine is going to want to share 1 of its electrons, and it's got 1, 2, 3, 4, 5, 6. Because you can see here, it's got 1, 2, 3, 4, 5, 6, and it's going to share this 1 electron with oxygen. And then hydrogen is going to share its 1 electron, and it's going to have just nothing else around it. So it should look like this. Okay, and if we count up our electrons, okay, you can actually add up to what it should be. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and that's important to keep track of because chlorine has 7, oxygen has 6 electrons, and hydrogen has 1. So it's going to be 6 plus 7 is 13 plus 1. So we're going to get 14 total, and that matches up with our drawing. Okay, it's always important to come back and count up your electrons in your diagram and make sure it adds up with the electrons, because sometimes you'll draw a dot structure and you'll be like, whoa, I'm missing 2 electrons. Where are they, and why did I put them in? Okay, this one's rather simple, so it's kind of obvious to kind of count them out and see where my electrons are. And the reason and how I know how many electrons I have is because of where it is located in which group. Okay? So as you're going through this, this takes practice. Okay? Actually, let's just do one more for the sake of it. Let's do one more. Let's say we have nitrogen, N2. All right, nitrogen has 5 electrons around it, and it wants to form 3 more bonds. So 1, 2, 3. It wants 3 more electrons to be like neon's configuration. So it's going to want to form 3 bonds. And if we look here, we can kind of just glance at it and go, well, these lone pairs aren't going to want to bond, but these single electrons will, and they both have 3. So that means we can form a triple bond, right? Because this one will pair with this one will pair with this one, and then these ones will pair on the outsides. Okay? These will bond with each other. And it's going to have a lone pairs on the outside. All right? So this is a triple bond example. This molecule is actually the reason why it's been so difficult to create fertilizers. One of the primary ingredients in fertilizers is nitrogen. And this triple bond is very hard to break. It's very strong. And there's a guy named, what's his first name? But we call it the Haber process. It's named after him. Haber, he's the one who came up with the idea of how to break these bonds and then combine them to make ammonia. So pretty cool subject. Maybe we'll talk about it in class. So anyhow, all right, let's keep going. Let's talk about electronegativity and bonding. So let's look at this image in our book. All right. Here we go. All right, new subject. We're going to switch gears for a second and we'll come back and apply it all together. So electronegativity, let me write this in your notes, okay, is the ability of an atom, of an element, to attract electrons toward itself in a chemical bond. Okay? And elements that tend to be, we've broken it up into givers and takers, right? Nonmetals are takers and the metals are givers. So you can assume that elements that are non-metal-like are going to have a much greater, higher electron affinity. They're going to be wanting to take electrons from other atoms, while the elements on the other side of the table are going to be very happy to give them away. Okay, so they're not going to be attracting electrons anytime soon. So these ones are going to be taking them. And we can actually classify a bond just by using these figures here. And we actually subtract these numbers for each bond to tell me what type of bond is it. Is it a covalent bond? Is it a covalent bond? And there's actually 2 different types of covalent bonds. There's called polar covalent and nonpolar covalent. So this diagram, I'm not expecting you to memorize this. Okay, you will have this available to you when you take your test and when you calculate these bond strengths. Okay, so let's take a look at this image and appreciate it for what it is. Okay, you can think of atoms as giving and taking electrons. All right, you can think of it as a tug-of-war game. So if we have 2 teams here, like 2 different atoms, and they're pulling equally on each other, all right, we get a nonpolar covalent bond. Okay, and if one team tends to be a little stronger than the other team, and they're still sharing, they're still kind of, it's not like quite broken, it's called a polar covalent bond. So they're just tugging it a little bit more than the other team is. And when one team completely pulls the other team across this line and takes its electron, essentially, we call it an ionic bond. So come down here and I want you to write down these definitions for polar and nonpolar covalent bonds. So a polar covalent bond is a bond in which electrons are shared, but not shared equally between the atoms. Okay? And then its number is between 0.4 and 2.0. Okay. A nonpolar covalent bond is a bond in which the electrons are shared equally. Nonpolar covalent bonds have minimal electronegativity difference, 0.4 or less. And you said it says difference, it's because we're subtracting the 2 atoms that we're comparing. Okay, so let's go back here and let's look at our oxygen water example. So we have oxygen and hydrogen. So we're going to examine this bond right here. So oxygen, its electronegativity value is 3.5 and hydrogen is 2.1. So if you subtract that, that's going to be about 1.4. it's 1.4. Let's just, yeah, I'm looking at an example, but we'll just use this one, okay? So we've got 1.4 is our difference. So based on our definition of polar and nonpolar, where does 1.4 sit? Okay, let's put this back up. Sorry, I'm moving things around. All right, so 0.4 to 2.0 is a polar covalent bond, while a nonpolar covalent bond is something that's less than 0.4. This is definitely greater than 0.4, and it's not greater than 2, so it's right in the middle, or not in the middle, but more on the upper end of a polar covalent bond. So that means oxygen and hydrogen don't share equally. This oxygen is actually pulling the electrons closer to itself. So it looks more like this. In our minds, we think of it, oxygen is sharing with hydrogen. But it actually looks more like this. The oxygen is pulling the electrons closer to it than hydrogen is. It's sharing unequally between these two atoms. Okay? Let's look at another one. We have that nitrogen example. All right? We have two nitrogens forming a bond, and nitrogen's electronegativity value is 3.0. And this one is 3.0. And if we subtract them, we get a difference of 0. So is that less than 0.4? Right? If it's less than 0.4, then it's nonpolar. All right? They're poling at the same rate. So there's two examples here. We've got one that's polar and the other one that's nonpolar based on our electronegativity difference values. Now, if you took something like NaCl, okay, ionic bond, its difference is going to be sodium is 0.9 and chlorine is 3.0. All right, that's a difference of 2.1. And if you notice, if it's above 2.0, it's an ionic bond. So essentially, the sodium, its electron, is being completely taken from chlorine. They're not even sharing. So that is actually how we define what an ionic bond is because the electron's taken. All right, it can either be shared equally, it can be shared not quite as equally, but they're still sharing, one's hogging it. And then lastly, there's the idea that an electron could be completely taken from the other atom. Okay. All right. So you're going to need to know how to calculate that using these trends. You do not have to memorize this. All right. There's going to be a reference sheet for this that you can be able to calculate the electronegativity differences. All right. Let's talk about polar molecules, and then I'll finish up with geometry. So we're going to jump ahead just a little bit. Okay. All right. Now let's kind of get into the idea of polar molecules. Let's use this example right here. Let's go down and use water first because we've talked about it. So we've got oxygen and hydrogen, right? And we know that they're not sharing equally because we've calculated it, right? It's 1.4. Okay, that falls in my polar range, which means my oxygens are going to be hogging my electrons. And because they're hogging electrons, okay, and they've got lone pairs, because the lone pairs, what charge are they? They're negative. And if oxygen is even pulling those electrons kind of unfairly toward itself, oxygen is going to be partially negative, while hydrogen is going to be partially positive because its electrons are being taken. All right, and if you notice, there's this little symbol here. Okay, we draw it like this. It's kind of loops around like that. It's kind of almost completing in a figure 8. Right? That means partial. So this is partially negative and this is partially positive. Okay? When we looked at NaCl, the reason they stick together, let me find my card, I got it on here. The reason they stick together is because sodium is losing its electron and it is positive and chlorine is negative. They are fully charged and they're being attracted to each other because of these charges. While water, on the other hand, they're still sharing, so it's more of like a partial negative and a partial positive. Okay, it's only a part. And we draw these little dipole arrows, okay, signifying where the electronegativity, where the electrons are going. So if we look here, the hydrogen is the more positive side, so we're going to draw our T, and then we'll draw an arrow to where the negativity is, where the partial charge is. Okay, partial negative charge, I'll say that. So, and if you look here, we can actually draw this as right in the center because they're both pulling kind of on angles to each other. And so we actually would just draw it right in the middle of this. Okay, so it's showing that this is the positive side and this is the negative side. We call this the dipole. And then here's an image of it to show you the unevenness of it. So this is going to be positive, all right, and this is going to be negative side here. Okay. You can think of the same thing with hydrogen and fluorine. So the electronegativity difference between hydrogen and fluorine is, I think, 1.9. All right, it's almost ionic. Okay, but now it's still polar covalent, so they're still sharing, but fluorine is going to be hogging the electrons, and hydrogen is going to be giving it away, so it's going to be a little more positive, and the fluorine is going to be a little more negative. So we're going to have partial positive, partial negative. So you draw this dipole right here, this arrow, it actually tells me that this side's positive and this side's negative. Okay, you don't need to necessarily draw it out like this with these partials, like up here. So that's why this symbol is pretty useful, because it can tell me where the pole is going. Okay? All right. And I'll just talk about it briefly. When some molecules, they actually will cancel each other out. See how this carbon dioxide molecule, where the dipoles are pulling away from each other? All right? Because they're pulling away from each other at equal poles, it actually cancels out. We're not going to spend a lot of time talking about this, but it's just good information if you want to read it. All right, lastly, let's talk about geometries. Okay, there's 6 geometries I need you to memorize, all right, based on molecular shapes. Okay, and these molecular shapes are formed between covalent bonds. Okay, not ionic bonds. Okay, ionic bonds don't have shapes. They're just attracted to each other because of charges. So if we have 2 electron pairs, they're going to form a linear relationship. If we've got 3 electron pairs, all right, so for example, we have something like nitrogen, it's going to want to form 3 bonds. It's going to form something that looks trigonal planar, okay? And if you imagined this shape, it would look like 3 in a, sorry, I'd say this. Trigonal is referring to, like, tri is 3, okay? If you can think of it as a 3-pointed triangle, and it's planar, meaning it's flat. It doesn't come out at you in 3D space. Okay? And then there's some that have a lone pair of 1 lone pair, and it's got 2 covalent bonds. We call this bent. Okay? The idea of identifying the shapes is when you look at a compound like, let's just do water again. If I've got H2O, right, and it looks like this, what would I call the shape of this compound? Or if I had carbon dioxide, it looks like this. Right? What would I call this shape? And if you look here, for carbon dioxide, we've got 2 bonds being formed and 2 atoms, so it looks a lot like, if you look at this example right here, come on a page here, you're going to see that this has a linear shape. But this one down here has 2 lone pairs, and it's forming 2 covalent bonds. What shape would it be? And you can kind of look down here and say, well, it probably is bent, right? And bent can come in 2 different examples. So this one has 2 lone pairs, and this one has 1 lone pair. And if you notice, how it says 1 and 2, I drew in these lone pairs. Your book won't have them in there, okay? But I drew mine into my book, so I can kind of see that, okay? All right. Yeah, and I think that nitrogen example I said earlier was not a good example, because nitrogen typically forms a lone pair, right? We've seen that in our examples just when we're going through it. Let me see if I can find one here. Right, for example, if we've got nitrogen, I've gone through all my cards, let me find another one. Let's do this one. So if we've got nitrogen forming 3 bonds with hydrogen, right? 3D shape, it kind of looks like a pyramid, and then on top there's a little lone pair. All right? What the book tells you a little bit about, but not really well, is that this lone pair actually pushes pressure on all of these bonds. So this lone pair actually takes up like a lot of space, and it's pushing down on all the other ones. So that's why these are actually bent. It's because these lone pairs are actually pushing down on my example here. Okay. All right. A common example of tetrahedral, something that has 4 sides, is methane. So CH4. All right. So if I were to draw this, it would be a carbon with 4 hydrogens around it, like this. All right. You can also draw it like this. So you have carbon. We have 1 going up, 1 going to the side, and then we can draw kind of a box like this, or triangle, and fill it in. And then I can draw some dashed lines going backwards. So this is referring to depth. So this is coming out at you, and this is going behind the page. Because in this tetrahedral, it's a three-dimensional object. It is not flat. It's not a two-dimensional object. It's three-dimensional. So when we draw it in our notes, sometimes we can draw it like this, where we have dashes that work our way out. And then sometimes we can draw it with a box coming out at you, like this. This works too, but this gives you a little bit better image of it in three-dimensional space. Okay? And there's no lone pairs. Okay? It's just bonding 4 different times. All right? And if it has one lone pair and it has 3 bonds being formed, we call it pyramidal, because it looks like a pyramid. And then bent is either 1 or 2 lone pairs bending 2 covalent bonds. Okay? So I expect you to memorize these these 6 different shapes. All right? As I butchered my explanation of this, okay? I want you to recognize that how many covalent bonds are being formed, and the lone pair's influence on those bonds, okay, and what's causing them to make this shape. All right, and that's part of the reason. Let me just give one last example, and then I'll be done. Okay, and when we have water, some students will ask, well, why don't we draw water like this? It's got 2 lone pairs. It's got water H's on each side. It totally satisfies. We've got the octet rule being completely filled with hydrogens and the oxygens. But the reason is because these lone pairs will put pressure and they'll pinch these bonds. So they'll actually configure themselves to form this. H and H. And it's going to actually push down on those bonds and push them down. Okay? So it's not going to look like this. It's going to look like this. And it comes with practice. All right? This is just going to be trial and error of you putting together molecules and me helping you see where your faults are. Okay? So keep that in mind. You're not going to get it on the first try. It's going to take some time to how to correctly orient them and put them in the correct way. Okay? All right. And we also call this VSEPR theory, or VSEPR theory. Okay? I want you to write down this definition. So bonding pairs of electrons and lone pairs of valence electrons repel each other and push each other as far away as possible to minimize electrostatic repulsions between them. So these are the shapes that are going to be formed as atoms share electrons based on the repulsions of those electrons and their charges. Okay? All right. Thanks again for watching. Until next time.